Hello everyone, my name is Kumar Aditya, and in this video I will demonstrate the volt-second balance principle using a buck converter example. So I have created this buck converter schematic here in the LT Spice, and I have input of 48 volt, and I am using a switching frequency of 40 kilohertz. That is switching time period is 25 microsecond. And if I run the simulation, on the top this green trace is my input voltage, which is 48 volt, and output is approximately 19 volt in a steady state. So this converter has certain transient interval, and after transient state is over, the circuit reaches the steady state. Now in the second plot, this is the current flowing through the inductor L4, and this third plot is the voltage across the inductor. Now volt-second balance principle says that for a periodic current, average voltage across an inductor is 0. That is, if the current flowing through the inductor is periodic in nature, then average voltage across the inductor should be 0. Now let's see whether it is happening in our converter or not. So I will first show it in the transient state. So this is my transient waveform, right? And if I consider one switching interval of 25 microsecond, so from here to here, this is my one switching interval. So this is 25 microsecond, and in this switching interval we can see that current is not periodic in nature. So during the start of the interval current is 0 amp, but at the end of the interval current is around 3.8 amps. So this is certainly not a behavior of a periodic waveform. And let's see whether the voltage across the inductor due to this current is average voltage is 0 or not. So average of this voltage pattern can be calculated by calculating the area under the curve. So this would be, let's call this shaded region as area A1, and we also have this area A2 below this 0 volt line. So average of the voltage in this particular switching instant can be given by A1 minus A2 by time base, which is 25 microsecond. And certainly A2 is very small compared to A1. We don't have to do the exact math. We can just observe that this area A2 is very small compared to A1. So average is not equal to 0. It is certainly greater than 0. So therefore you can see we are violating the volt-second balance principle here. Since current is not periodic, average voltage across the inductor is not 0. Or in reverse or in opposite manner, we can say that since average voltage across the inductor is not 0, current flowing through the inductor is not periodic in nature. And since this average is greater than 0, this current keeps increasing, right? So if we can draw the envelope over this transient, we can see that current is rising. But eventually it comes down because this is a properly designed converter. The converter reaches its steady state very quickly. So current does not get to a point where it becomes very dangerous for this inductor. And that's the one of the design consideration when you are designing any DC to DC or switch mode power supply, that you make sure that your transient period does not last very long, right? If your circuit should reach a steady state as fast as possible, and the peak value of current during the transient interval. When you are selecting the component, you make sure that those components such as this switch, this inductor, capacitor or diode, whatever, can tolerate the peak value of current flowing through your converter during the transient interval. Now let's see the steady state interval. So I will zoom on to this interval here, and let's consider this particular switching time period. So from here to here, you can just by observing you can tell that this current is periodic in nature. So at the start of the time period, current has the value of 0.5 amp. It rises to a certain value, then but at the end of the time period, it again comes back to the same value of 0.5 amp. Now this current is periodic in nature. Therefore, if we take the average of the voltage across the inductor in this switching time period, we will get the average equal to 0. Now I will not do the math, I have already verified it. You can also verify it in your circuit, but this area A1 will cancel out this area A2. Therefore, average value of the voltage in this switching interval will be 0. Now again in the reverse manner, we can say if the average voltage across the inductor is 0, then current flowing through the inductor will be periodic in nature. So two important things we learned from this example is that it's very important when you are designing a DC to DC converter that you always follow the volt-second balance principle, and for that purpose your transient interval should be as small as possible. Your circuit should reach steady state as fast as possible, and component selection should be proper. That is, you make sure that the peak value of current or voltage during transient is tolerated by your inductor, switches, and diode, whatever component you have in the circuit. So I hope this is useful to you, and you get the idea what I was trying to explain. If you have any question, you can leave that in the comment section, and you can watch my video on volt-second balance principle. I will leave the link in the description. So see you in the next video. Bye bye.